have it be like the second example, maybe
Like what was the second? Oh yeah.
for cooling
Uh-huh.
the water.
Yeah, right. Right. Okay. So um, last time we did this example. This. So we did this example um, where we had an ideal Rankine cycle. Um, water is the working fluid. Which is pretty typical. Um, and we had saturated vapor um, entering the turbine at a pressure of 8.0 megapascals. And then we had saturated liquid exiting the condenser um, at 0.08 megapascals. And then we were told that the net power output is 100 megawatts. And the parts that we did so far, we wanted to calculate the efficiency, and we got 0.371, so 37.1% efficiency. Second, we got a back work ratio of 0.00831, so about 0.8% of the energy that we produce from the turbine needs to be used to run that pump. Then we wanted to calculate the mass flow rate. That's m dot. And we got 104.74 kilograms per second. Then we wanted to calculate the rate of heat. I'm going to write this QH dot. The rate of heat entering at the boiler, entering the working fluid, is 2.70 times 10 to the 8 watts. And then the rate of heat leaving the working fluid at the condenser, and that we got 1.70 times 10 to the 8 watts. Okay, and now we want to ask one more question. Oh, and before I go into this, when you saw this problem, how did we go about this? What's the main thing that you're trying to do in these kind of problems? Do you remember? It's basically always the same approach. You don't even have to look at what it's asking until, yeah.
We label the circuit.
Okay, yeah, that's right. But and I guess what I'm getting at is everything that we do is to try to find like a set of values to start with. And those values are the enthalpies, the specific enthalpies at each one of those states between the processes. Okay, so like you see a problem like this, ideal Rankine cycle, you don't even have to bother to look at what it's asking you. You just know that you're going to be trying to calculate those specific enthalpies. Okay, you can't really do anything until you have those. And so now there's one more question we can ask. So part F, if the cooling water in the condenser comes in at a temperature, an input temperature of 15 degrees Celsius, and leaves at an exit temperature of 35 degrees Celsius, what's the mass flow rate of this cooling water? So the idea here is the condenser needs to cool down this working fluid. The way it does it is it passes cooler water around it, like a radiator or something, like a radiator in a car. And that cooling water is flowing. It's not in contact, like it's not mixing with the working fluid, but it's moving through a pipe around the working fluid in like a in a conducting material, something that can conduct heat, like say copper or something, And so in a simplified view, you can think of this sort of like this.
Do we think of it as a steady state as well?
Yeah, so I'll tell you all that. And yes, steady state. It is. We are going to assume steady state. So the working fluid is going one way. This is the condenser. So this is the working fluid. And the cooling water is moving the other way through this condenser, and they don't mix with each other. To make this more accurate, you would really have the cooling water pipe sort of break out into a bunch of little capillary pipes that would surround the working fluid to maximize the heat transfer between those two. Anybody have any questions about what I'm trying to picture here? So you're trying to maximize the surface area between these two pipes as much as possible so that as much heat as you can get moves from the working fluid into the cooling water. Okay. And so we are going to think of the entire condenser as a control volume. We're going to assume that it's steady state. It's rigid, so we're going to, all it's doing is trying to let heat transfer occur between these two pipes. So we're going to assume that there is no work done by this control volume. And then here's one that at first seems a little surprising. But we're also going to assume that there's no heat transfer for the control volume. Well, the whole idea of a condenser is heat transfer. But notice that all of the heat transfer we want is occurring inside our new control volume, which is the whole condenser. Are you with me on that? So we do have heat transfer from the working fluid to the cooling water, but that's all inside the condenser. Okay. So there is heat transfer. But it all happens inside our control volume. And in this control volume analysis, remember that Q dot is referring to heat transfer between the system, between the control volume and the surroundings. So we don't have any of that. Okay. We'll also assume, no. So these are pretty standard. We're not going to worry about changes in kinetic energy or changes in potential energy. So let's go through this analysis now. So we'll start with the full first law for control volume. So dE dt is equal to Q dot minus W dot plus, I'll just write this as M dot because it's steady state, times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. Steady state says that this is 0. No changes in kinetic or potential energy, so those cancel and those cancel. And then we have these. And now we have to think about breaking up okay, we have this new thing that says 0 is equal to M dot times the quantity HI minus HE. Okay. But now notice that we have 2 inlets and 2 exits and 2 mass flow rates.
Is this like the temperature equilibrium problem, but just continuous?
Well, we're using the first law, so I guess I don't think we did that way. I don't think we used the control volume approach. But so we're just going to keep using the first law like this, but we just have to think about what all our inlets are, what all our mass flows are. So now remember that we have 2 inlets, 2 exits, and 2 mass flow rates. So I'm going to rewrite this as 0 is equal to the mass flow rate of the working fluid times, the inlet specific enthalpy of the working fluid minus the exit specific enthalpy of the working fluid, plus the same thing for the cooling water. We have the specific enthalpies for the working fluid at every state, right? We needed that in order to do all of these first problems. So what states are we talking about here as the inlet and exit for the working fluid? So this is where it's helpful to remember these diagrams, try sketching them out from memory a couple times. Just try to burn it into your brain. But we know that we have so our state 1 goes through the turbine to state 2. Then it goes through the condenser to state 3. Then it goes through the pump to state 4. All this is irrelevant at this point, but I got to finish my picture now. So this is the boiler. From state 4 to state 1. So, and we're going around this way. And so coming into the condenser is state 2, leaving the condenser is state 3. So we have 0 is equal to the mass flow rate for the working fluid times the specific enthalpy at state 2 minus the specific enthalpy at state 3 plus m dot for the cooling water times the quantity specific enthalpy at the inlet for the cooling water minus the specific enthalpy at the exit for the cooling water. Now we can fill some of this stuff in. So we have 0 is equal to the mass flow rate for the working fluid. Every calculation we've done up to this point has been referring to the working fluid. So here we have, where is it? Mass flow rate, 104.74. So 104.74. And our specific enthalpies from before, I guess I didn't write those down. Oh, well, those are the ones from the condenser. So let me just make sure I get the signs right here. So for the condenser, m dot times H2 minus H3 is equal to QC dot. See that? And so since I have QC dot listed here, m dot times the difference of those enthalpies is just 1.70 times 10 to the 8th. And now this is equal to m dot for the cooling water times the quantity HI minus HE. So how are we going to get this difference in specific enthalpies? So now all we need is HI for the cooling water minus HE for the cooling water. We're trying to calculate that m dot. So remember that, so this is for a um, this cooling water is liquid the whole time, so it's incompressible. Um, and if you think about a change in specific enthalpy, think about the definition, that's equal to the change in specific internal energy plus the change in pressure times volume.
And so the control volume V is equal to the change in V is equal to zero.
Change in V is equal to zero, that's right. Yep.
That would be just change in specific enthalpy.
Yeah, so we're gonna assume that this is constant pressure. And so what we get is that the specific enthalpy is just equal, the change in specific enthalpy is just equal to the change in specific internal energy. And so now we can write, so du, the change in U, is equal to C times the change in temperature. We've done that a bunch of times before for incompressible materials. And so, and this is our delta H, which is what we want. And so delta H is equal to 4186 times the change in temperature. At the exit, it was 35 degrees Celsius. At the inlet, it was 15 degrees Celsius. And so we get a change in specific enthalpy of um, so that is, oh, we want inlet minus exit. So I have those reversed, sorry. So we have 15 minus 35. And can someone punch that in? I think you get something like negative 83,000. What? 83,000 what?
720.
Okay. So now I'll go back up to this equation. 1.70 times 10 to the 8 is equal to negative of m dot for the cooling water times negative 83,720. And you get that m dot for the cooling water is equal to about 2,030.58 kilograms per second. Notice that that's a much higher flow rate. That's something you're going to see, I think, in every problem you do. So this is a much higher flow rate than the working fluid.
Well, isn't that like good because the temperature only changes a little bit?
Mm-hmm.
So that if there's like a lot of heat very quickly, then the water can just absorb it.
Yeah, right. That's right. It's like the liquid version of wind chill. You know, it's using convection to get that heat out of there. So much higher mass flow rate. than the working fluid. Any questions about that? Okay, let's go to number 3. We have an ideal Rankine cycle. And so let's think about what this process looks like. So here we have the boiler. Here we have the turbine. Condenser. And notice for the start, we're not thinking about the cooling water at all. We're just thinking about the working fluid. Later on, you can think about the cooling water if it asks for it. And then here we have the pump. And that's state 3 to state 4. And if you look at it in a temperature specific entropy diagram, it looks like this. So here's our state 1. We have an isentropic process as it goes through the turbine. Then it goes through the condenser. Then it stays a liquid. It goes from a saturated liquid to a compressed liquid as it goes through the pump. And then there's the last stage. Okay, so from this, the benefit of this diagram is that you can tell what the phases are of all of these things. And I'm going to write out state 1, state 2, state 3, state 4. From state 1 to state 2, that's going through the turbine. That's isentropic. From state 2 to state 3, that's going through the isobaric condenser. From state 3 to state 4, that's going through the isentropic pump. And then from state 4 back to state 1, that's going through the isobaric boiler. And so what do we know? It's water, so we can use that if we need to look anything up on the website. Saturated vapor enters the turbine. So entering the turbine is state 1. And it has a pressure of 16 megapascals. Um, the condenser pressure is 8 kilopascals. So the condenser is from state 2 to state 3. That's isobaric. At state 2, this is a saturated mix. And we're given that the pressure at state 2 is 8 kilopascals. Notice that the way that turbine works is this drastic pressure reduction. You start with this high pressure that you need to drive the turbine. That pressure goes down by the end. State 3, what's the phase of state 3?
Saturated liquid.
Yep, perfect. Saturated liquid. And the pressure, since this was isobaric, is still 8 kilopascals. And we're given that the mass flow rate entering the turbine is this. And it asks us a bunch of stuff. I mean, basically, we're just going to use what we have here to try to figure out all the specific enthalpies at these states. Then we know we'll be able to start to work our way around. There's one more thing that we know before we start thinking about kind of thermodynamics. We know it's an isobaric boiler going from state 4 to state 1. We have the pressure at state 1, so we know that the pressure at state 4 has to be, well, let me write the phase here since I did for all the other ones. So state 4, this is a compressed liquid. But because it's isobaric, we know that P4 is 16 megapascals. Okay, so what can we start to look up? We can look up anything in state 1. It's a saturated vapor, and we have one property, and so what do we want to look up for state 1? What's going to be helpful here?
Entropy.
Yeah, perfect. Yep. We want to look up the specific entropy here because that's going to be the same specific entropy at state 2. Why do we care about the specific entropy at state 2?
Because when you have both pressure and specific entropy, you can get the other properties as well. Is it you said state 2?
Yeah, state 2, right. So this is a saturated mix. And yeah, that's basically the idea. What we want here is we want to come up with the quality in this mix. And so once we have the specific entropy at state 2, we can look that up. So so the specific entropy at state 1, let's look that up. We want international units. This is water. This is a saturated vapor. And so the quality is 1. And the pressure is 16 megapascals, which is 1600 kilopascals. And so the specific entropy is 6420, and that is 6420. That is just in joules. Okay. 6420. So S1 is 6420 in SI units. And so now we can use that to say that S2 is 6420. And now we can calculate that quality. So at state 2, to find this quality, we have 6420 is equal to X times the specific entropy for a saturated vapor at 8 kilopascals. So we have water. We want a quality of 1. Pressure is 8 kilopascals. And so the entropy is 8227. And then plus 1 minus the quality times the specific entropy for the saturated liquid at that pressure. So I just have to change the quality from 1 to 0 to get the value for the saturated liquid. And we get 592.5. And now we just have to calculate that quality from that equation. So 6420 minus 592.5, and then divided by 8227 minus 592.5. And I get 0.763. So what percent of, at state 2, what percentage of this mass is vapor? Yeah, right. So 76.3% is vapor, the rest is liquid. And now we're going to use that to find the specific enthalpy at state 2. So the specific enthalpy is equal to 0.763 times what the specific enthalpy would be for a saturated vapor. So we'll go back in here. My cursor. We want the vapor here. And the specific enthalpy is 2576 times 10 to the third. Plus 1 minus 0.763 is what, 0.237 times the specific enthalpy for a saturated liquid at that pressure. So I just change this to a 0. And we get 173.8 times 10 to the third. And
Did
so,
we find the page for state one yet? We found the total, right? One more time.
oh yeah, we can look that up anytime. I haven't done that yet, I guess. But we have everything we need to just look that up. And so H2 is 2006.7 times 10 to the third. This is joules, yes, joules per kilogram. States 1 and states 3, we can just look these up. So a saturated vapor at 16 megapascals so saturated vapor at a pressure of 1600 kilopascals is 2793 times 10 to the third. So 2793 times 10 to the third in SI units. And at state 3, we have a pressure of 8 kilopascals, a saturated liquid. We've seen this already. 173.8 times 10 to the third. And then, as is often the case, the last one we have left is state 4. State 4 is always more complicated because it's not at saturation. But we have a couple possibilities here. If we're given a temperature, we can look this up. If we're not, we can use the fact that from state 3 to state 4, it's incompressible. So we can use this equation that says H4 minus H3 is equal to the specific volume times the difference in pressures. So H4 minus H3 is equal to the shared specific volume times the pressure at 4 minus the pressure at 3. And so that says that H4 is equal to specific volume times the quantity P4 minus P3 plus H3. Um, and so we could look up that specific volume, or you could assume that it's going to be somewhere pretty close to 0.001. Either one is fine with me. But so how would you look this up? How would you look up a better value for little v?
You just find it off the properties. So it's incompressible. So
Yeah, so you could, the pressure. All that matters is the temperature for that specific volume when you're dealing with incompressible materials. Nothing matters except temperature. So you can, for the pressure you have, treat that as the pressure in a saturated state. Just go to quality and, make it something so that you're in that saturated state. And then just look at what the temperature is. And then at that temperature, you can get that specific volume. So I'll just do it. We're almost done. So 0.001 times P4 was 16 times 10 to the 6. P3 was 8 times 10 to the third. H3 was 173.8 times 10 to the third. And so H4.
Professor?
Yeah.
So, like, water is like 1,000 liters per meter cubed, right?
Let's see. The density is 1,000 kilograms per cubic meter.
And like,
so a big giant box is.
The changes seem to always, like, they end up not being significant enough to matter. So can we
Right.
use that as just
Yes, on tests and stuff in this class you can always use that, but you should have in the back of your mind how you would get more precision if you had a meaner teacher.
Okay.
So 189, 792. Okay, so now we have all four of the specific enthalpies. And now we can, now we're in business. Now we can just start checking off these things that it's asking for. So ... That's not really a good way to answer your homework, ... but yeah. Okay, so that's it for today.